Eric Burgess here. A random sample of 55 cars in the drive-thru of a popular fast food restaurant revealed an average bill of $13.11 per car. The population standard deviation is $4.87. Estimate the mean bill for all cars from the drive-thru with 99% confidence. Okay, there's two ways to do this problem that are commonly taught, and the first way is the calculator, the second way is using the formula. I'm going to do the calculator way first, and then we will do it using the formula to check our answers. So if you use either one of those, you should be covered. Now in the calculator, you can actually just click on, and first I guess I should show you how we can identify the problem that we're doing. So it asks us to estimate something. Where does it say that? Population estimate right there. Estimate the mean bill. So this immediately kind of clues us in that we're doing a confidence interval for a mean. And then the 99% confidence right here is another kind of giveaway that it's a confidence interval problem. So what we're going to do is we're going to come into our calculator for the first way. We're going to go to stat. And if you actually go over to tests, there's going to be some confidence interval stuff. Now it just says interval, but we're going to come down to those. Now there's a couple different ones. So we have some proportion intervals. You've got some t and z intervals. So we need to come back to our problem and determine, are we doing a z, t, or proportion? And so we look at here and we say, what kind of standard deviation do we have? Well, we have a population standard deviation. So since we have the population standard deviation, we can use a z interval because we've got that one. If it was a sample standard deviation, then we would go to a t interval. But we have a population standard deviation, so we can use z. So we're going to choose that one. And okay, so you're confronted with data or statistics. We have the statistics here. We were given a mean, we were given a sample size, we were given the standard deviation. We didn't have any raw data to work with. So we're going to go with stats. Our population standard deviation sigma, well, that is going to be right here, $4.87. So we put in $4.87. Our mean was $13.11. And so we put that in, $13.11. Now keep in mind, this is a sample mean. It came from our sample of 55 cars, right? We want to use our sample information to estimate the true mean of all cars that come in. And so our n, that's 55. We just plug that in. Our confidence level is right here. It's 99%, so we change this to 0.99. And we hit calculate. And it spits it out for us right here in interval notation. So this is the lower value and this is the upper value. And the way we would write this sort of in math is we would write the lower value first. So 11.419. And then in between this value is the mean. Oh, am I writing in blue? Here, let me write in black so it's different than the problem text. So we have 11.419. And then the mean is in the middle. So this is how we write mathematically in the middle. The mean is between 11.419 and 14.801, just like what we have here. And we should write out in words sort of what this means. This means we estimate with 99% confidence. We estimate with 99% confidence. I'm just going to write confidence that the true mean for the average bill is between this $11 and, if we round, $11.42 and $14.80. So that is what we are estimating the true mean to be. And so if your professor wants you to write out like a sentence sort of stating how to interpret this, this is the sentence that you would write. This is what we think the true mean is. Because, right, we are asked to estimate the mean bill for all cars through the drive-thru. And that's what it is for all cars here. And so we cover the all cars by saying the true mean that's another way of saying sort of everyone. So you could say instead of the true mean, you could say that the mean for all cars is, if you feel a little more comfortable writing it that way. Now, okay, the formula. So there's another way to do this. It's the actual formula that the calculator is using. So when we do this process, what we're doing is we're doing a point estimate based off of the sample that we have. So right, first we get a sample estimate, and that sample estimate is our average. And then we're going to have some error. So there's the mean in the middle, and then there's going to be some error below. So it's going to be our average minus the error. And then we're going to have some error above. So it's going to be the error above. So we put a plus. So this pushes our estimate below and above this population mean. And then the error itself is we characterize it using the distribution. We make an assumption about the distribution. And we were told that we have a population standard deviation. So we're allowed to use a standard normal distribution, which tells us we can use z-scores. So we're going to do minus z. And now this is kind of like a two-tailed test. There's things above and below. And so we split our alpha into two pieces, right? Because if we were to draw out our chart here and look at this thing, there's going to be an area of that we are very confident. We are 99% confident. And then there's going to be a 1% area that we're not confident in. It's been split in half. There's half down here, 0.05, and 0.05 down here that we are not confident about. Right? And when we add them together, we get 0.1. Oh, I made a mistake here. It should be 0.005. 0.005. And just to sort of show you, if we were to take, right, we would have 0.01 is left, right? That's 1%. And if we were to divide this by 2, we get 0.005. So when we add these together, we'll get the whole 100% of the curve, right? Because this is really 0.99. And so that's the idea. So we take our z, and for the area below, it's actually our alpha, which is this area that we're not sure about, and we split it in half. And then we're going to multiply it by some error characterized by our data set, and that's going to be the standard deviation divided by the square root of n. So this thing right here is E. And what we're going to do now is we're just going to put that, on the other side. So we're going to do the mean is in the middle, the true mean. And then we're going to have x bar plus z of alpha over 2 times sigma over rad n. Now this, you may just go to your formula sheet and just find this, but that's sort of the explanation of why this is the formula that we choose. And so let's go ahead and just plug these values in. So we know for our x bar, we already had all these things picked out from before. We had an average of 13.11. So we have 13.11 minus, we need to find a z of alpha over 2. There's two ways to do it. I'll show you the calculator and then I'll show you the chart. So z of alpha over 2, well, we know that we need to find it for 0.005 because that's our alpha when we split it in half. And so we can go and do an inverse lookup because we know the area and we want the z-score. So we're going to do an inverse lookup to get the z-score. So we go to second distribution, and then we're going to go down to inverse normal. It's going to look up z-scores according to areas. And we want to give it 0.005. With our standard deviation, because we're on a standard normal, our mean is 0 and our standard deviation is 1. Because we're using z-scores. That's always the case for z-scores. And we get this. So we get minus 2.5. We're going to round up. So 2.58. And the reason we only need one of these, so we have to look it up again over here. But because the distribution is symmetric, it's going the negative versions here and the positive versions here. So it's actually going to be the same number. Now, if we wanted to find this in the chart, we would just look up as an area 0.005, and we should get negative 2.58 as a result. So let's go ahead. Let's go to the standard normal chart real quick. And we want to look in the area section for 0.005. So let's see here. Here's 0.004. Let's keep going. We want to go up. And so let me move the calculator out of the way here for a second. And looking here, we've got 0.005 and then 0.8, 0.00494. So this is away by 8, where this one's only away by 6. So we're going to go with this one right here, just because it's a smidge closer. It honestly doesn't matter all that much which one you get, but as long as you're really, really close. And so look at that. We get negative 2.58. If we were to look at the z-score that it produced, we get negative 2.5 and then 0.08. So negative 2.58. So we get the exact same score using the chart. And then again, we can say because it's symmetric, we just take the plus and minus of that. So that's how you find those values using the calculator in the chart. And it's a good way to check your work. So up next, we have our standard deviation. That's 4.87, just continuing to fill in the formula. The square root of n, our n was 55. And now we have the mean. And then it's the same thing, 13.11, except for now we're adding the error. So it's the exact same expression, just added. So 2.58, 4.87 over the square root of 55. Now we just put this thing in our calculator. We're going to get two values with the mean in the middle. And let's do it. So in the calculator, let's grab this, pull it over here. We've got 13.11. So we type 13.11 minus 2.58. And now we have a parenthesis. And now we have a fraction. Okay, so there's a couple ways to put this in the calculator. I'm going to do it the fancy way. We've got an F1 here. So we're going to hit alpha F1. And it brings up a fraction option. So we choose that. And then we choose 4.87 divided by the square root of 55. So we hit the blue key and then the square root key, 55. And we close it. Now I'll show you the other way to put it in with this side. So we hit enter and look at that. We get 11.41. And what did we get for our previous answer? Let's scroll up here. 11.41. So we got the exact same thing, and then we would write the same conclusion down here as an interpretation. Now let's do the other side, and I'll show you the way to do it if you don't have a calculator that can do fractions. So we have 13.11 plus 2.58, and we again put parentheses, but now we want to do this stuff inside. So it's going to be this top part divided by this bottom part. So it's going to be 4.87 divided by, and then I'm going to put parentheses to tell it to do this bottom part separately, just because it's a good habit to just put things you want to be done individually in parentheses. And I'm going to put a square root sign. So we're going to do the square root of 55. I'm going to move out from under the square root and close the parentheses for the lower half, and then close the parentheses for this big set. So it's like I put extra parentheses around this guy. And that's it. So we're going to go ahead and hit enter. And we get 14.80, which is the exact same thing that we get here. And so we would write on ours, right? We got 11.419 and we got 14.804. So we got the exact same things, and we would write the same conclusion. But that is how you do this. If you have any questions about this, let me know, subscribe, and we'll catch you in the next problem.